So good evening. My name is Kathy Duffy, for those who don't know me, but so many of you have been here over and over. We're glad to have you back, but we have some newcomers, and you're very welcome. As director of the Institute for Religion and Science at Chestnut Hill College, a regional center for exploring science and spirituality, I would like to welcome all of you to our Sugarloaf campus and to this evening's lecture. As many of you know, the Institute aims to promote the constructive engagement of religion and spirituality with science and technology, and to encourage dialogue in these areas, that is, interfaith, multi-science, and civil. We sponsor lectures, a reading circle, and other events and resources. Do check our website for a growing number of videos of past lectures and for a list of relevant books that are housed in our library. Also, you can follow us on Twitter to access more information about the science and religion dialogue and what's happening in the field. We also have a blog that is, once in a while anyway, someone writes to it, but you could always send us something to post. Also be sure to sign in at the back at the desk if you aren't already on our mailing list. So if you didn't get a mailing from me, please sign up, and then at least you'll find out what lectures we have ahead. I think we have a very exciting program this year. Of course, tonight's program is really wonderful. But upcoming programs include Mark Schultz from Bryn Mawr College, who's going to talk on the science of mindfulness, what we know and don't know. Mark Wallace from Swarthmore, who will be looking at the spiritual need, the spirituality needed to engage the environmental problem. And Janet Mock, the former director of the Leadership Conference of Women Religious, who will share something of the process that the officials of LCWR used in their conflict with the Vatican. And Jesuit Tom Rees, who will reflect on Pope Francis' encyclical, Laudato Si. So please join us for all of these events if you can. But this evening, it's my great pleasure to introduce Dr. Michael Mann, Distinguished Professor of Meteorology at Penn State University, with joint appointments in the Department of Geoscience and the Earth and Environmental Systems Institute. Dr. Mann also directs the Penn State Earth System Science Center. Dr. Mann is well qualified to speak with us this evening. With undergraduate degrees in physics and applied math from the University of California at Berkeley, a master's degree in physics, and a PhD in geology and geophysics from Yale University, Mann presently uses theoretical models and observational data to better understand Earth's climate system. Dr. Mann is the recipient of many awards for his work in climate science. Among them, the Hans Oeschger Medal, is that right? I knew I would forget, of the European Geosciences Union, the National Conservation Achievement Award for Science from the National Wildlife Federation, and Friend of the Planet Award from the National Center for Science Education. Dr. Mann is a fellow of both the American Geophysical Union and the American Meteorological Society, the author of more than 180 peer-reviewed and edited publications, and 2 books, Dire Predictions, Understanding Global Warming, and The Hockey Stick and the Climate Wars, Dispatches from the Front Lines, as well as being a participant in a number of government panels and committees on the topic of climate change. We hope to have someone here selling his books, so I imagine that will happen afterwards. If anyone's interested, and Mike has agreed to sign the books afterwards, so be ready for that. As we know, climate change is a critical issue in today's world, important enough for Pope Francis to write an encyclical on the topic. Tonight, Mike, we hope to learn from you more about the science behind this concern and perhaps to understand better what each of us can do to stem the tide of destruction. And for the rest of us, please join me in welcoming Dr. Michael Mann. I'm going to mess this up.
Well, thanks very much. It's a pleasure to be here with you tonight. And it really is a unique time in history to be talking about the issue of climate change, both from the perspective of the underlying science and the issue of faith and religious tradition. With the Pope's encyclical, we have seen a sort of a new framing of the issue of climate change, not just an issue of science and economics and politics, but we've seen the issue of climate change framed as an issue about ethics and morality. And I think I hope we'll have an opportunity to discuss that maybe a little bit in the Q&A, the sort of how both the science and faith come together in informing our approach to dealing with climate change. I'm going to talk about this mostly from the standpoint of the science, the underlying scientific evidence that climate change is happening, that it's due to human activity, the impacts that it's already having, and the projected impacts that it may have if we continue on this course that we're on. And I will talk a little bit about solutions as well. What can we do to solve this problem? The first point I want to make is that the underlying science, despite what you might think from some of our public discourse, which portrays the issue of climate change often as contentious and controversial. In reality, the science isn't controversial. The basic underlying principle, the greenhouse effect, we've known about that for nearly 2 centuries. Joseph Fourier, the same scientist who gave us the law of heat conduction, understood that certain gases in our atmosphere, greenhouse gases, warm the planet. And we've mostly just been refining our understanding of that physics and that chemistry over a period of nearly 2 centuries. The fact that we're increasing the concentrations of these gases in the atmosphere, again, that's not controversial, it's incontrovertible. In fact, this plot here, which I put together a couple years ago, is already so out of date that you have to add another vertical tick mark to the scale because we exceeded 400 parts per million CO2 in the atmosphere a few years ago for the first time in what we believe is literally millions of years. Okay, so we are engaged in this unprecedented experiment in how we are changing the composition of the atmosphere. So that's really all you need to know. The greenhouse effect, it's nearly 2-century-old physics and chemistry. The fact that we're increasing the greenhouse effect substantially is incontrovertible. What we wouldn't be able to explain as a result of that is if the Earth were not warming up. But it is. The observations tell us the globe has warmed a little less than 1 degree Celsius over the past century. Now, the critics, and there are critics when it comes to the science of climate change, some of you may have encountered that, well, they'll point to the end of this record and they'll say, well, look, you know, it was really warm in 1998, we hadn't beat that record, you know, maybe global warming has stopped. You've heard that a lot lately, that global warming has stopped because, you know, maybe you can convince yourself that if you draw a short trend line here that the warming rate has dropped off. Well, it's not true. 2014, turns out, was the warmest year on record. And that's actually what the graph looks like. And 2015 is going to be up there, roughly, with 9 months already in. We're fairly certain that 2015 will actually beat 2014 by a substantial amount. So, in fact, the warming trend continues unabated. There are year-to-year fluctuations because of things like El Nino and volcanic eruptions, but the warming trend continues unabated. And again, the critics will tell you, well, you know, we don't trust any of those thermometer records. You could throw them all out. Throw out all the thermometer records. I could show you dozens of independent lines of evidence that tell an internally consistent story of a planet that is warming up in a climate that is changing much as we expect it to, as we continue to increase the concentrations of these greenhouse gases in the atmosphere. And that's the sort of evidence that has led the very conservative IPCC, the Intergovernmental Panel on Climate Change. This is a group of hundreds of scientists who assess the entire peer-reviewed literature over a period of 5 years, every 5 years, and write a report that represents our best current assessment of the science underlying climate change. And the IPCC said that the warming of the climate system is unequivocal in their last report. As I said, this is a conservative body. It's literally a sort of lowest common scientific denominator of what hundreds of scientists can agree upon. And so when the IPCC says that the warming of the climate system is unequivocal, it means that the warming of the climate system is unequivocal. Scientists aren't debating that. Now, is that all invalidated because we've had a few cold winters? Hey, it was cold this morning, this part of Pennsylvania. And if you believe our potential next president, Donald Trump, a few cold days somehow invalidate everything that I just told you. Is that true? Well, everywhere I go now, I try to get a hold of the records. What's happening to unusually cold temperatures? And everywhere I go, the data tell me that they're getting less and less common, as you would expect as the Earth warms up. And that's true here in Philadelphia. So yes, anecdotally, we still get cold days here and there during the winter. And there is an interesting discussion taking place within the scientific community about whether it's possible that the jet stream is changing in a way that gives us more variation, more day-to-day variation in temperatures during the winter than we used to see. That's a possibility. There's some science that suggests that might be true. But the unusual cold, rates of unusual cold are dropping, rates of unusual warmth are increasing, and that's true in Peoria, Illinois. So if it's true in Peoria, turns out it's true just about everywhere. Well, another line of evidence, and it's one that relates to work that I did a decade and a half ago, involves extending the temperature record back in time, because we only have about a century of widespread thermometer measurements. If we want to get a sense of how unusual the warming trend is in a longer-term context, we have to turn to indirect measures of climate, what we call proxy data, like tree rings and corals and ice cores. And again, a decade and a half ago, my co-authors and I published this graph in the journal Nature, and then we followed it up with an extension back to the last 1,000 years a year later. It ended up being featured in the summary for policymakers of the 2001 IPCC report, and it quickly became an icon in the climate change debate because it told a simple story. You didn't need to understand the physics of the climate system to understand what this graph was telling us, that there really is something unusual about the warming that we're seeing today, and by inference, it probably has something to do with human activity, the Industrial Revolution, the increase in greenhouse gas concentrations from fossil fuel burning. But as happens to graphs and symbols that become iconic in the climate change debate, they get attacked. And the hockey stick, and my co-authors and I have been rather viciously attacked at times by those looking to discredit this iconic graphic in an effort to somehow convince the public that the entire weight of evidence for concern about climate change is dependent on one 15-year-old study, when in fact, even if you didn't have the hockey stick or the numerous other studies that have all come to the same conclusion now that the recent warming really does appear to be unprecedented, even if you didn't have any of that evidence, we would still know, based on the fundamental evidence I presented during the first few minutes of this talk. Simple physics and chemistry we've known for 2 centuries. Irrefutable measurements of how we're changing the composition of the atmosphere, and equally irrefutable measurements of how the climate is responding to it. Even if we didn't have the hockey stick or the hockey league, the multiple reconstructions that come to this same conclusion, we would still know that human beings are warming the planet and changing the climate. But the hockey stick was oh, yes, and I'll point out that because of all those other studies, the IPCC has now concluded that, in fact, the recent warming probably is unprecedented even farther back, at least 1,400 years. There's some tentative evidence now that the warming spike that we're seeing now is unprecedented in tens of thousands of years. Now, again, because the hockey stick became a symbol in the climate change debate, and there have been numerous efforts by climate change contrarians and deniers to discredit it. I've had interesting experiences over the years involving tussles with senators and House committee members and fossil fuel industry front groups and various individuals and organizations that have been attempting to sort of discredit the science of climate change. And I talk about those experiences in my book, The Hockey Stick and the Climate Wars. But that's not what this talk is about. I want to talk now about climate models. And again, the critics will sometimes tell you that everything we know about climate change, our entire understanding, the entire basis of our evidence that humans are changing the climate is based on climate models. And that's simply not true. In the first few minutes of this talk, I presented you the evidence that we are changing the climate, warming the planet. And it didn't depend on climate models. Now, we do use climate models because, as I said before, we're engaged in this unprecedented experiment with the one planet that we have. And it's an uncontrolled experiment. If we want to pose and test hypotheses about the climate, how might the climate have changed if we weren't increasing greenhouse gas concentration through fossil fuel burning? What's the effect of natural factors? If we want to pose these sorts of questions and test them, then we need to use some conceptual framework that formalizes our understanding of how this system works, and that's what a climate model is. A climate model has an atmosphere just like a numerical weather forecasting model. The models that we use to forecast the weather, well, they're like the atmospheric component of a climate model. But when you talk about climate, when you're talking about longer-term changes, then it isn't enough to just say what the atmosphere is doing. You need to know what the ocean is doing, and you need to know what the carbon cycle, the global carbon cycle is doing, and you need to know how all of this is interacting with incoming radiation from the sun and how greenhouse gases are interacting with the heat energy that the Earth tries to release out to space. And so we take the physics, we take the chemistry, and even some of the biology that's necessary to describe this system, and we solve the equations. We do the math. That's what a climate model is. Now, some of you will recognize this. Anyone want to tell me what we're looking at? Yeah, some people look at that and they say the Seinfeld restaurant. I myself look at that and I say NASA Goddard Institute for Space Studies, because there's a climate modeling center in the upper floors of this building, the NASA Goddard Institute for Space. I did a sabbatical there, actually, back in 2004. So I got to go to the Seinfeld diner for work every day. It was a lot of fun. But back in 1988, 3 years before the Seinfeld show went on the air, Dr. James Hansen, who was the director of the NASA Goddard Institute for Space Studies, was doing experiments with a climate model. In fact, he was making predictions with a climate model that was quite crude by today's standards. And as we all know, predictions are hard, especially about the future. It's not Yogi Berra, it's Niels Bohr. Niels Bohr. Predictions are hard, especially about the future. Physicist Niels Bohr. And that's right. So what Hansen did was to make some predictions in 1988 about what would happen in the future. He ran his climate model 3 different times, with 3 different initial conditions. You don't always get the same simulation, just like weather has a chaotic component to it, climate has a chaotic variable component to it. And then he projected forward. Now, Hansen wasn't a fortune teller. He didn't know what we would choose to do. He didn't know if we would choose to greatly curtail our burning of fossil fuels or accelerate our burning even beyond the historical trajectory. But he could look at 3 different scenarios. You could say, well, what if we greatly curtail our burning of fossil fuels? The model predicts that we'll follow that purple line. What if we accelerate our burning of fossil fuels beyond the historical trajectory? And what if we do something in between? Well, it turns out if you look at what we actually did in terms of our burning of fossil fuels and the pathway that we followed, it actually corresponds most closely to that scenario B. So that was his prediction of the warming that would be expected given what it is we actually ended up pursuing, the fossil fuels that we actually ended up burning. That's what he predicted would happen. And that's what actually happened. Pretty successful prediction 2 decades into the future. Now, if you're a critic, you might look at that and you might see, the flaws. You might say, well, okay, if the model's so great, how come it missed this huge event right here in 1991, 1992, where the globe cooled by nearly half a degree Celsius? And it's true that Hansen didn't know in 1988 that Mount Pinatubo would erupt in 1991. And when it did, it would put large amounts of particulates into the lower stratosphere, where they block out some of the incoming sunlight for several years and cools the Earth by a few tenths of a degree Celsius for a few years. What Hansen did realize is that it takes about 6 to 9 months for that volcanic cloud to spread around the globe and begin to have a cooling effect. So he had time to run another climate modeling experiment, and he predicted that the globe would cool by a few tenths of a degree Celsius for several years, as it did. So what might have looked like a flaw in the original prediction was actually an example of another successful test. And needless to say, if you look at the various reports of the IPCC, there are hundreds and hundreds of pages of model validation exercises. In short, there are reasons to take these models seriously. They have been vetted. They have made some impressive predictions in the past. So let's use these models then to test some hypotheses. And again, if you're a critic, you might say, well, okay, so the globe is warmed. How do we know it isn't due to those natural factors? We've seen that volcanoes can cool a climate. If you have some change over time in the number of volcanic eruptions, that could lead to a change in temperature. There are small but measurable changes in solar output. We can see them with satellite measurements. We can actually measure them back into the past with sunspot data. So how do we know it isn't those natural factors? Well, we can put them in the models. We can take the climate models. We can drive them with just the natural factors. And that's what happens. When you drive the models with just the natural factors, the globe actually wants to cool over the latter half of the 20th century because we had a number of big eruptions like Pinatubo, El Chichon in '82. Solar output was flat or even declined slightly according to the satellite measurements. So the globe actually should have cooled if it was just natural factors that were at work. It's only when we add the human factors, in particular the increase in greenhouse gas concentrations from fossil fuel burning, that we are able to explain the warming that we've seen. And that's the sort of evidence that has led, again, the very staid, the very conservative IPCC that doesn't like to go out on a limb to state that it is extremely likely that human influence has been the dominant cause of the observed warming since the mid-20th century. And even here, the IPCC is being its characteristically reticent self, because if you read the technical chapters of the report that underlie that statement, what you'll find is that the IPCC actually estimates that we're most likely responsible for more than 100% of the observed warming. And what that means is, you already saw, the natural factors were pushing us in the opposite direction, and we warmed in spite of them. Okay, so what about our future? What about our future projecting forward? Well, to a great extent, we control our own destiny. If we could stop emitting carbon into the atmosphere right now, we would most likely avoid a 2 degrees Celsius warming of the globe relative to pre-industrial time. That's an important number. 2 degrees Celsius is where many of the scientists who study the impacts of climate change will tell you we really start to see the most severe impacts of climate change and potentially irreversible changes in the climate system. On the other hand, if we continue with business as usual, well, then we're somewhere in the range of 4 to 5 degrees Celsius by the end of the century, 7 to 9 degrees Fahrenheit warming of the planet. Twice that much in the Arctic because of the amplifying effect of melting ice and the greater absorption of the solar heating. Well, it's actually instructive to look at what that pattern is over time, because the whole globe doesn't warm uniformly. This is a simulation, and we're in the 1950s. Now we're going to continue. We're increasing greenhouse gas concentrations. We're going to more than double them by the end of the 21st century. And you can see the Earth is warming up. There's still cold winters in North America here and there. We're now into the future, okay, 2016, 2017. Yeah, you still get some cold winters in North America, but they get fewer and farther between and less severe, and the warmth gets greater and more pervasive. And there's more warming over the continents than the oceans, and most of us live on the continents, so we actually see more than the global average warming. It's important to understand. The Arctic, you can see, is warming even faster because of the melting ice and the amplifying feedbacks associated with that. And by 2200, we will have warmed 4 degrees relative to the 1950s, plus nearly 1 degree that we had already warmed by then, almost 5 degrees Celsius warming of the planet. But there are a few distinctive features. There's at least one distinctive feature that sort of sticks out like a sore thumb. Does anyone see it? Yeah? Where's that? Greenland, south of Greenland, yeah. Something funny going on there. All right, remember that. We'll come back to that. Oops. Wrong direction. There we go. Well, we don't just care about warming. We don't just care about temperature. We care about all the other changes in climate that will impact us and other living things. Water, we rely upon water. Other living things rely upon water. What happens to rainfall? Well, it turns out that the models tell us that rainfall, in a sense, is a zero-sum game. The dry regions of the subtropics expand as the atmospheric circulation changes in a warmer climate. So the sort of belt of deserts expands to higher latitudes into North America, parts of Europe. Rainfall actually increases in the tropics. Where you have rising motion in the atmosphere, which is the tropics, and then another tendency in the subpolar regions where storm systems are found. Where you have rising motion, you actually tend to get more rainfall out of that rising motion because there's more moisture in the atmosphere. So as long as you have lifting and you're able to take the moisture and cool it and form precipitation, you actually get more precipitation because there's more moisture in a warmer atmosphere. So you see more rainfall in the tropics, more rainfall at the high latitudes, less in the subtropics. So you might say, oh, it's a zero-sum game. We can just move the water around, we'll be okay. It's not that simple, though. That's what soil moisture looks like. It decreases just about everywhere. And what's happening here, even in some of the regions that see increased rainfall, the soils are warmer. They're evaporating more moisture into the atmosphere. So even in some regions where you see an increase in precipitation, ironically, you lose even more through evaporation. And so soil moisture decreases everywhere. Drought becomes more pervasive just about everywhere over the continents of the world. Sometimes we are called alarmists by our critics because we're supposedly overstating the changes in climate that we're seeing or we can expect to see. But the data say just the opposite. Here's one example, Arctic sea ice. The shaded region is what the models say should be happening. The red is what's actually happening. We're seeing Arctic sea ice decrease way ahead of schedule relative to what the climate models predict. So quickly, in fact, that some experts are concerned we'll see ice-free conditions at the end of the summer in the Arctic in a matter of decades, not half a century or more, as the climate models have tended to say. Well, there are other things that are happening when it comes to the melt of ice that are potentially even more problematic, because sea ice, when it melts, doesn't raise global sea level. The ice is already floating on the ocean. But ice sheets, continental ice sheets, like the Greenland ice sheet and the Antarctic ice sheet, when that ice melts, it does raise sea level. And what we're seeing is that, once again, things seem to be ahead of schedule relative to what the climate models predicted. The climate models said we probably wouldn't see net loss of ice from the 2 major ice sheets until midway this century. But the satellites tell us we're already seeing net loss of ice. In fact, recent studies suggest that we may now have committed, we may have warmed the Southern Ocean enough that we've destabilized the ice shelves that support a large part of the West Antarctic ice sheet. That's the part of the West Antarctic, the Antarctic ice sheet that's close enough to sea level that it could easily calve into the ocean. And based on the warming we've already seen, there are some studies now that suggest that there's nothing to hold that back. We've now destabilized those ice shelves. That inland ice will eventually surge into the ocean. We'll lose most of the West Antarctic ice sheet. That's enough to give us 12 to 14 feet of sea level rise alone. We don't know how quickly that will happen, but we're now pretty sure that we have passed that tipping point, okay? So there's the first example of a tipping point. point of no return. Once you destabilize those ice shelves and that ice starts flowing into the ocean, there's nothing you can do to stop it. Turning the temperature back down, lowering the CO2 won't stop it. Once you set that process in motion, it has inertia. It becomes what we know as a positive feedback, and it feeds on itself. If you look at the effect of sea level rise, which is already a foot off the U.S. East Coast, almost a foot off the coast of New Jersey and New York City, and you look at the effect of climate change on tropical storms and hurricanes, it turns out it's sort of a double whammy when it comes to coastal threats, because we have rising sea level, and that means that when you do have a storm surge, it's sitting on top of a higher sea level. And the storms, hurricanes in the Atlantic, appear to be getting both more intense and larger as a result of climate change. And both of those things contribute to large storm surges. Sandy gave us a record storm surge because it was both a strong hurricane, the strongest hurricane north of Cape Hatteras in October in history, and it was the largest storm of its superstorm of its type in history. It was very large and it was very strong, and that means it built up a very large storm surge. And so in an article that we published just a few weeks ago in the Proceedings of the National Academy of Sciences, we showed that the effect of sea level rise and intensified and larger hurricanes has already taken an event that would have been a 3,000-year event. Before global warming, Sandy should have been a 3,000-year event. It shouldn't have happened more than once in 3,000 years, a 14-foot storm surge at Battery Park, New York. Now it's more like a 100-year event. Climate change has turned that into a 100-year event. If we continue with business as usual fossil fuel burning and we warm the planet 4 to 5 degrees Celsius by the end of the century, then a Sandy-like storm surge becomes a one every few year event for New York City. And obviously at that point, you're talking about withdrawing. We're literally withdrawing from our coastlines because cities like New York City are no longer viable, or Miami Beach, or other cities that are faced with the twin threats of rising sea level and increasingly strong storms. Well, I talked about one example of a tipping point, which is the destabilization of the ice shelves and the sea level rise that potentially locks in place. There are other examples of potential tipping points, and there's one that I used to be quite skeptical about. Many of you will be familiar with it in the form of, anyone here see the movie The Day After Tomorrow? The collapse of the ocean circulation, it leads to another ice age and giant tornadoes destroying LA and 3 huge hurricanes covering the entire northern hemisphere and an ice sheet forming in 3 days. The movie violated many principles of atmospheric science that I hold quite dear. That having been said, there is a grain of truth to the movie The Day After Tomorrow. I used to be skeptical about this. I used to be skeptical about the possibility that we could see an abrupt slowdown in this ocean circulation pattern that we call the conveyor belt. Sometimes we associate it with the Gulf Stream, but it's actually a broader circulation pattern that continues up into the North Atlantic, and it delivers a fair amount of heat up towards Europe and Iceland and Greenland. It keeps the North Atlantic warmer than it otherwise would be. And if you shut off that ocean circulation pattern, you could actually get a return to glacial conditions over a large region in the North Atlantic. That's the grain of truth to the movie The Day After Tomorrow. And something like that actually did happen at the last ice age. As we were coming out of the last ice age, and we melted all this fresh water that flowed into the North Atlantic. The fresh water is light, and so it acts as a lens. It caps the sinking motion that otherwise drives this conveyor belt, and it shuts down that conveyor belt circulation. And it happened at the end of the last ice age, and we actually saw the North Atlantic sort of continue, the North Atlantic actually return to glacial conditions for about 1,000 years or so until it completely came out of the ice age. So the movie, of course, nothing that happens in the movie The Day After Tomorrow is likely to happen in the real world. But what we are seeing is a grain of truth to what the movie predicts. If you look at the trend in global temperature over the past century, there is this small region in the North Atlantic that's actually cooling. We saw that climate model simulation. We saw that cooling region in the North Atlantic. It's the same thing. The climate models predict that that region cools as this ocean circulation slows down. Now, the climate models don't predict that to happen until really the end of the century. In an article we published earlier this year in the journal Nature Climate Change, we showed that it's already happening. This is the actual 20th century observations. And if you measure the temperature change in that region as an index of what's happening with this ocean circulation pattern, there's a pretty sharp decrease over the last century. In fact, there was a very sharp blip in the 1950s and 60s and a little bit of a recovery. But once again, we're sort of beyond where we think we should be based on what the climate model simulations say. Perhaps the actual ocean circulation pattern conveyor belt is more sensitive to climate change than the models indicate. Now, we won't get another ice age. As you saw in the animation earlier, you just get this one region in the North Atlantic that cools, but it turns out that that shutdown of that ocean circulation pattern actually influences the marine productivity in the North Atlantic. It could be a problem for the productivity of fisheries in the North Atlantic, which we rely upon. And interestingly enough, if you slow down that ocean circulation pattern, it turns out that you actually tilt the sea level in such a way that sea level rises even faster along the U.S. East Coast. So if that ocean circulation pattern collapses, we see even greater sea level rise along the U.S. East Coast. So there are reasons to be concerned about that tipping point as well. And just recently, there were a series of articles about this, a couple that ran in the Washington Post, because that's the pattern of 2015 so far. Warmest year on record. It's certainly going to be the warmest year. We know that now, just based on the data that are in. And record temperatures over a large part of the globe, but that region in the North Atlantic, the cold blob as we call it, record cold right now. It's the coldest it's ever been in that region. So we really think we're seeing this. I was skeptical that we would see this quickly. And I was convinced by the work that my collaborators and I did as I became involved in this, and we looked into it. It really appears to be happening. Well, so projections of the future. Again, business as usual. We'll see 4 to 5 degrees Celsius warming of the planet, 7 to 9 Fahrenheit warming of the planet by the end of the century. Now, in some sense, what we're talking about at that point is a different planet. To quote James Hansen, who I mentioned before, the NASA Goddard scientist who sort of first alerted the public to the dangers of climate change back in the late 1980s, he has described a 4 to 5 degrees Celsius warmer world as a different planet, a fundamentally different planet than the one that we're used to, the one we're familiar with, the one that we grew up on. Now, I used to end this particular sequence with the polar bear on the ice floe, because it's actually the law. You have to show a polar bear on an ice floe and talk about it. Now, I think by making the polar bear the icon of climate change, we have inadvertently, the scientists, communicators of the science, when we use this as the symbol, as the poster child of climate change, we inadvertently present climate change as a very exotic problem. It's something way off in the Arctic, impacting animals that I've never seen in the wild, I only see in zoos. It makes it feel like a very distant problem, I think, in some sense, when in fact it isn't. And so everywhere I go now and I talk about climate change, I talk about how climate change is impacting us now where we live in a visceral and palpable way, whether it's in the UK where the flooding that they had last winter. You want to talk about conservative scientists. The UK Meteorological Office are among the most conservative. They really are very conservative in how they frame climate change impacts. And so when the Met Office said that those floods wouldn't have happened in the absence of climate change, in the absence of a greater amount of moisture in the atmosphere because of the warmer atmosphere, you can be pretty certain that that record flooding that they saw wouldn't have happened in the absence of climate change. I am quite convinced that the record drought that we're seeing in California, which is the worst in at least 1,200 years according to tree ring records, that we can see very clearly the signature of human-caused climate change. Now, there's an interesting debate that's broken out within the scientific community, and a legitimate debate about whether the particular pattern of the jet stream that has deprived California of rainfall in recent winters, whether that can be attributed to climate change. It's a pattern that can happen naturally. There is also evidence that as you melt away the Arctic sea ice and you allow more heat to escape from the Arctic Ocean, you can actually change the pattern of the jet stream. And more than a decade ago, there was a study by a leading scientist that said that the decrease in Arctic sea ice would cause the jet stream to change, the winter jet stream to change in a way that would bring the storm track north of California. And that is what we're seeing. And so there's a debate about how much of it can be attributed to climate change, how much of it is just natural climate variability. But what you can't debate, even if we can't confidently attribute the low precipitation associated with the northward migration of the jet stream in recent winters, even if we can't attribute that to climate change, we know that California had the warmest year on record last year. And we know that means that there was a potential for greater amount of evaporation of whatever moisture the soils did have. And so that clearly was impacted by climate change. And the record low snowpack, which meant that there was little, if any, runoff in the spring and summer, which is what California relies upon for agriculture and for their water supply, that too was clearly related to climate change. And so at least two of the three factors that have come together to give us this perfect drought in California, we can talk about how climate change impacted that. I actually think that the jet stream pattern is being impacted by Arctic sea ice in the way that some scientists have said, and that too there's a climate change component to that as well. Florida, I've given several talks there over the last year or two, and there's this tide that they get every 2 or 3 times a year when the lunar cycle lines up the right way. They get this king tide, this very high tide, and they've always gotten king tides. But what didn't always happen was that when they came, they flooded the streets of Miami. And now, in the most recent king tide, which came a few weeks ago, it wasn't just Miami, it was a large part of Fort Lauderdale. And so this is the way we're going to see the impacts of sea level rise along our coastal, along our coastlines. It isn't just going to be this slow, gradual inundation. It's going to mean that the extreme events are going to be more extreme. And those events that would have been nuisance floods before are now going to be catastrophic floods. And pretty soon we're once again forced to retreat from our coastlines. And that's a very expensive proposition. Here in Pennsylvania, some of the record heat that we've seen in recent years, the 2012 heat wave, we saw several Pennsylvanians perish in the heat associated with that heat wave. We've seen more frequent extreme heat. If you look at what the climate models tell us, they tell us that if we continue on the course that we're on, then by the end of this century, what today we call a record heat wave will be what we then call a summer day. Most of the summer will be about as hot as the hottest days we just about ever see today. That's the sort of future that we face if we do nothing, if we just continue with business as usual. We don't have to just continue with business as usual. We can do something about this. Now, there's a certain amount of climate change that we're going to have to deal with. A certain amount of additional warming, a certain amount of sea level rise that's already baked in. That it's going to happen no matter what we do just because the climate system has inertia. It's like a locomotive. It doesn't stop when you slam on the brakes. It can take a mile down the tracks before it stops. The same is true with the climate system. So yes, we are going to have to adapt. We're going to have to find ways to manage diminishing water supplies in many regions, find ways to continue to keep up agricultural yields despite the predicted decline in productivity with increased warming. And we're going to have to find a way to deal with encroaching seas, whether it's building levee systems or other ways of managing flooding, or ultimately what we call managed retreat. We just move away from our coastlines. But we can't. Actually, before I go on, in a 4 to 5 degree warmer world, if that's where we go by the end of this century, the sorts of adaptive measures that people are talking about are not going to be adequate for us to deal with the impacts that we'll see. Now, some argue that we can engineer our way out of this. Okay, we can mess around with the climate system in some other way, and maybe we'll get lucky and we offset global warming. And there are elaborate schemes for shooting particles into the stratosphere, putting mirrors in space, fertilizing the oceans, dumping large amounts of iron into the oceans to try to fertilize algae activity and take CO2 out of the atmosphere. In every single one of these cases, the law of unintended consequences reigns supreme. We could easily end up making many of these problems even worse. In fact, there's some evidence that the shooting these particles into the stratosphere, if you do it wrong, what happens is you offset warming in some regions, you actually cause other regions to cool, you could actually warm Greenland even faster, and you dry out the continents more. So when you look at these schemes in more detail, again, many of them come with some real potential unintended consequences. And arguably, a much safer option is to just stop that behavior which is leading to climate change, to stem our growing emission of carbon into the atmosphere. And to do that, there really is no magic bullet. There are all sorts of things that we can do in our personal lives to decrease our carbon footprints, and we should all be doing those things. Many of these are no regrets strategies. They make us, they save us money, they make us healthier, and they cut our carbon emissions. We should all be doing those things, but voluntary measures alone aren't going to give us the sorts of cuts in carbon emissions that we need if we're going to avoid a catastrophic warming of the planet. If we're going to do that, we're obviously going to need to do something about the way we go about getting energy. And there's a very worthy debate, very worthy policy debate to be had about how we do that, about what measures we put in place, what approaches we take to try to meet growing global energy demand in a way that doesn't fundamentally degrade our climate and our planet for our children and grandchildren. There's a worthy debate to be had about how to solve this problem. There is no longer a worthy debate to be had about whether we have a problem. And so it's really time to move on to the discussion of solutions. And I think one of the promising developments, again, to sort of come back to where we started, was that this problem is starting to be framed not just in terms of science and economics and politics, but in terms of ethics. And to me, it's very much an issue of intergenerational ethics. I have a 10-year-old daughter. I'd hate to think that we are mortgaging the planet for her and her children and grandchildren with what we're doing now. There's still time to make sure that we don't do that. And I think it's a matter of great ethical import that we do not leave behind a degraded planet for our children and grandchildren. So I think I'll leave it there, and I'll be happy. I guess we're gonna. I don't know how we want to do the questions.
How about if we take a couple minutes right there at the tables to talk about some of the issues, and then after about 5 minutes or so, you can ask Dr. Mann whatever you wish. Okay, so get your thoughts together at the tables. Okay.
Okay.
Microphone.
Just take it out.
Whatever you want to do. And then I have two students who are going to field the question.
Okay.
I'll try to print.
Okay, sounds good. All right, sounds good.
Okay, I hate to disturb your wonderful conversation, but let's take some time now to ask some questions. If you raise your hand, we have two students here who will come around.
Yeah, I have a question which arose up during the early part of your talk, and that is you showed a graph indicating the temperature versus time with different degrees of greenhouse gases as a parameter,
Right, yeah.
specifically showing different slopes. And then you indicated that the different slopes indicated, those are the different amounts of greenhouse gases involved. And then you stated that if you just left the system for it in its natural state, in fact, the temperature would go down. That's the way it went.
Are you
yeah.
referring to this plot here?
Yes, yes. You
Yep.
said you indicated that, in fact, if you leave it to its natural state, that line would go, the temperature would fall.
Well, no, it would avoid warming more than 2 degrees. So,
Because
yeah.
that's what
Yeah.
confused me. Because when
Okay.
you say it falls. Oh, you said. Oh, you mean it falls relative to 2 degrees?
It'll fall below 2 degrees, yeah.
Oh, okay. Because,
Right.
because then I'm just wondering, well, it should have reached equilibrium, and equilibrium will maintain it at a steady state, precisely as that shows.
That's right. So you can see
Yeah.
we've stopped emitting CO2, but the globe continues to warm a little bit because it's still approaching equilibrium, like we were talking about before. It's like a locomotive. The ocean is continuing to absorb heat from the surface, and so it takes a while for the surface temperature to stabilize. But when it
understand.
does, it'll be below 2 degrees for that
I-
scenario.
I understand. Thank you.
Have that graph where it went down from the volcanic emissions?
Oh, sure. Absolutely.
That's the one.
Yep. Yep. Yep.
Question back here.
Yeah.
We were talking at my table here about how our whole infrastructure, particularly in the United States, relies so heavily on fossil fuels, and that even though we've made choices, Prius instead of Buick, or natural gas instead of coal, it's still contributing to the problem. And then the, green energy sources, from what I understand, you can't generate that amount of energy that we need from those sources without it being fantastically expensive and costing resources to create. How do you envision bridging that gap? Yeah,
so there have been some really detailed studies of this. One in particular coming out of the Carnegie Institute at Stanford University, where they've looked at if you take existing renewable energy technology and reasonable assumptions about increased energy efficiency, sort of how long would it take us to get to, say, 100% renewable energy? And you're absolutely right. We couldn't do it right now. We couldn't even do it most likely in 10 or 20 years, probably 2050 or so. So what that means is that we need to find sort of a bridge to that future. We're not there yet, where we can get 100% of our energy needs from renewables. On the other hand, we can probably avoid so often this problem of 2-degree warming, sort of keeping warming below that quote-unquote dangerous level of 2 degrees Celsius. That requires burning less than 1 billion more tons of carbon. So we actually have a finite carbon budget, and we know roughly what that is. So in order to, if you want to think about how we would have to lower our carbon emissions by, the middle of the century, we would have to lower our carbon emissions by about 80% relative to 2005 levels. And so if you work it out, it's doable, but it would require massive investments in renewable energy. The interesting thing is that the market is already starting to solve this problem on its own. We're seeing renewable energy approach what we call grid parity with fossil fuels, even without a price on carbon. So just the efficiencies and economies of scale of that are arising from the manufacturing and deploying of of renewable energy, and the fact that China has invested so heavily in solar cell technology that now that's leading to cheaper solar panels around the world. We're already moving in the direction where last year, for the first year ever, we added more power generation capacity from renewables than we did from fossil fuels. It's the first time ever. The other thing that we saw was, for the first time ever, we had net economic growth globally without an increase in carbon emissions. So what that suggests is we're already starting to turn the corner, but as you allude to sort of do it fast enough to the point where we do keep warming below dangerous levels, we need to accelerate that process, and that's really why people argue that we need to put a price on the externality. The problem is that it's an unfair playing field right now because fossil fuels, you burn fossil fuels, it's doing damage to the planet, but that damage isn't internalized in the economy. The way you internalize that externality is by putting a price on the emission of carbon. And if you were to do that, then suddenly renewables become even more competitive and you move even faster in the direction you need to. So, there's an interesting debate right now about whether or not you can solve a problem like this within a free, a market-based economy. And Naomi Klein recently wrote this book, This Changes Everything, where she sort of argues that you can't. I disagree with her. I think that you can solve this problem within a market economy framework, but you need to put a price on the externalities. Another question? I'll let the students decide.
Yes, I found your presentation really interesting. Thank you for coming. And my question was, it seems like the climate change debate among science debates has been not only very deeply divisive, but also unusually public. I mean, there are debates over global public health, over food production and distribution. Why do you think the climate change debate has been really center stage in so many ways?
Well, it's a great question. And I think there are probably many factors you can point to. I think the elephant in the room is the fact that we are talking about the largest, most powerful industry that ever existed on the face of the planet being directly challenged, in this case, the fossil fuel industry. And it isn't just a theoretical construct. We know that they have literally spent hundreds of millions of dollars in a major public disinformation campaign aimed at manufacturing controversy and confusion about the underlying science. Now, I don't know if how many people have come across this story. It sort of started to appear in some pretty prominent media outlets. It led the LA Times last Sunday. So ExxonMobil, there was a study, it was a year-long investigative journalism project by a Pulitzer Prize-winning outfit called Inside Climate News. They're a little-known organization, but they won a Pulitzer Prize for their investigative journalism. And they got a hold of all sorts of internal documents, internal reports from ExxonMobil going back through the 1970s. And what they were able to lay out very clearly is that ExxonMobil's own scientists knew by the late 1970s that climate change was real, it was happening, it was being caused by the burning of fossil fuels, and their own scientists referred to the potential impacts as catastrophic. What happened subsequently is that ExxonMobil laid off that research division and instead decided to massively fund a disinformation campaign to deny any impact. If it sounds a little familiar, it's because, well, this is what the tobacco industry had done. It was the same playbook, some of the same players, some of the same paid scientist advocates who advocated for tobacco interests and denying the health impacts of their product are today paid by fossil fuel interests to attack the science of climate change. So we can't ignore the underlying politics in the elephant in the room, which is, now that having been said, I actually think that there are some players within the fossil fuel industry who are taking a more enlightened view about this now. And Shell recently has, argued in favor of pricing carbon emissions. I think we're starting to see a change even in the culture of at least parts of the fossil fuel industry. ExxonMobil right now is in damage control mode, and there are a number of prominent politicians now who are arguing that they are probably, they could be subject to RICO, civil RICO, just like the tobacco industry, racketeering. If you knowingly hide the negative impacts of your product from the public, that's considered racketeering. And there are a number of powerful politicians right now who are arguing that maybe ExxonMobil will be subject to RICO for that. Yeah. Oh, sorry. Sorry.
Yeah, I think my question is leading out from what's gone before about the forces. That's the causes of global climate change really are multifactorial, but it's interesting moving beyond fossil fuels and power sources and energy sources. I've read and studied that the number one thing that we need to do as a society and a culture and as individuals is to move to plant-based food. And that comes up against meat industry and whatnot, because when you think about all of the herds of cattle all giving off their methane and all of that, Time magazine, I think a year ago mentioned that, said that was the number one thing that individuals can do to wreak a change. But then once again, you're up against the powers that be and how people are used to thinking about their diet and all of that. I was wondering if you could comment on that.
Yeah, no, absolutely. And in fact, this comes up a lot now because of this movie Cowspiracy. And a lot of people have seen that. And you've seen Cowspiracy. I'm not making it up. Apparently, it's a lot of people have seen this, and it basically makes this point that this is a major source of our carbon emissions, eating meat. And there's certainly something to that. And it really does get at this issue of personal actions that we can take individually to try to lower our carbon footprint, and that's part of it, changing your diet. And we do our best to sort of have a largely vegetarian, low meat diet, and it's not for everybody, but if you can do it, it's a great thing to do because it does lower your carbon footprint. And if you look at our total carbon emissions, there really is no one magic bullet. I mean, they come from every sector of society. It comes from energy generation, it comes from transportation, it comes from industry, and it comes from forestry, deforestation, and it comes from livestock and farming. And because of the movie Cowspiracy, there are a lot of people out there who have come to believe that emissions based on livestock raising and consumption of meat are the major source, and that's not even close to being true. Fossil fuels are still overwhelmingly the source of our carbon emissions, but you're absolutely right. Every little, if you look at the pie of our carbon emissions, each one of these things is a slice, and it's something that we can try to tackle, and that's part of I think that is part of the solution.
I have two political questions, which I'd like your opinion on. One, do you think that the replacement treaty for the Kyoto Protocol is going to pass this December? That's one. And two, do you think it's possible that this country would pass a cap and trade?
So two great questions. It's very interesting. There's an outfit that actually has looked at, if you just take into account the voluntary commitments that are already on the table of all the participating nations going into the Paris summit later this year. It's actually fairly impressive. It takes us halfway from business as usual, 4 to 5 degrees warming, to where we need to go, less than 2 degrees warming. It turns out that it'll bring us to maybe 3.5. So it doesn't bring us to where we need to go, but just looking at the voluntary measures, the agreement between the U.S. and China, and now India has now committed to lower their carbon emissions the same amount that we committed to in our bilateral agreement with China. And so you've got the 3 largest emitters now making a major commitment. If you take all of the commitments on the table, we're actually halfway to where we need to be. And so I think there's some hope that in Paris, maybe with the right motivations, with a lot of the sort of the optimistic sort of developments that are already taking place going into that summit, that maybe we will be able to reach an agreement for mandatory cuts that do get us at least close to that. Maybe we don't get to 2 degrees. But if we get close enough, then there's something to build on, in the next several years. So, no, do I think that we're going to solve the problem all at once in Paris? No. Do I think we've already made some progress even going into Paris? Yes. Do I think we can make even more progress in Paris? Yes. So I think we're turning the corner. Now, the other part of your question was cap and trade in the U.S. So one of the interesting arguments that you hear by opponents to pricing carbon emissions is that, look at China. They're the largest emitter of carbon on the planet, and they're not doing anything. Well, that argument fell to the wayside over the last year because China is now implementing a cap and trade system. So China is investing more in renewable energy than we are. They've committed to pricing carbon in a way that we haven't yet. The Obama administration, through the Clean Power Plan and through tighter fuel efficiency standards, has made commitments to lower our carbon emissions. But without a congressional climate bill, we're not going to have an actual price on the emission of carbon. So China is ahead of us in several respects. And I think that starts to put some real pressure. Now, pressure alone may not be enough to take an intransigent Congress that is, fundamentally answerable to the Koch brothers at present. We're probably not going to see a climate bill pass this Congress or any Congress with a similar composition to this Congress. But things can change quickly in politics, and with a somewhat different congressional makeup, maybe we could see a climate bill pass within the next several years. We probably won't see it within the next 2 years. But with the progress we're seeing at the state level, the municipal level, and at the executive level, maybe if in a few years we can see progress at the congressional level, we'll be making the sort of progress we need to make. We're already making enough progress that we can actually go into Paris and say that we've made a good faith effort through, these new coal-fired power plant carbon emissions requirements and fuel efficiency standards. The Obama administration can go into Paris, with a pretty strong hand, which is something we didn't actually think was going to be true just a couple years ago.
Just to piggyback on the UN conference in Paris, I guess one question that's to be asked is what role the scientific community will play if the agreement, the voluntary commitments end up getting us maybe to 3.5 or something, when at least from what we're hearing is that it really needs to be below 2 degrees Celsius. And so I know the scientific community has been put in a position lately to have to take a more public role. And so will there be some organized effort on the part of the scientific community to say, well, it's nice that there's an agreement, but it's not enough, and we need to do something?
It's a great question, and it's a very delicate matter, really, because as a scientist, I'm painfully aware that what I really bring to the table is my authority as a scientist, not as a policy expert or an economist. And so it's always important, I think, when you do speak to policy and you do speak to the economics and the policy debate, to always try to be clear, when you're speaking, out of your expertise as a climate scientist, and when you're just weighing in as a citizen, as any of us, have the right to weigh in with our views and our opinions, wearing our citizen hat, and so I always try to clarify, when I'm speaking as a scientist and when I'm just speaking my mind as somebody whose views are informed by, an understanding of the scientific evidence. That having been said, I do think that, we do play an important role as advocates for an informed policy debate. I know there's some scientists who think, they see advocacy as a four-letter word, and they're uncomfortable with the notion of a scientist as an advocate. But I think we have to recognize that advocacy can mean many things. And if nothing else, certainly we're advocating for a fact-based discussion. I mean, we wouldn't be speaking out about the scientific evidence if we weren't advocating for an environment in which decisions were informed by, sober and objective assessments of the scientific evidence. And that means the scientific evidence of climate change that is happening, what the impacts are likely to be, and to some extent what we know the costs will be and the choices that we'll have to make. So I think it's appropriate for scientists to play that role. And in fact, I think that if we don't, then we leave a vacuum that will be filled by those with an axe to grind and those who don't necessarily have the best interests of the public in mind, but have the narrow interests that they're advancing in mind. So I happen to be a scientist, perhaps it's obvious, who does believe in the role of speaking out and informing the policy debate and weighing in when it seems appropriate. Not all scientists are comfortable with that, and not all should. Frankly, I have colleagues probably are best left alone in their labs working on science. That's what they like doing. That's what they do best. And it would be unfair to ask them to do more than that. So, I think there are roles for scientists who want to play a greater advocacy role in the discussion, and there's a role for scientists who don't. And I think we each have to, decide, where we lie along that spectrum.
So you had mentioned about the renewable resources for energy, and what we were discussing here is the issue that, like you're talking about, China's making advances with solar energy. What hasn't been advancing are batteries for storage of the energy. And how do you envision, because you almost are going to need like a major invention to make a huge change there? Is there any of the things that you're talking about are going to help push that? I don't know if it can
Elon
be done.
Musk. The Tesla electric, no, but the new battery, the new battery, the power, the Giga, what was it? So Elon Musk is investing, in developing, battery, industrial, sort of grade battery storage, and there's this new product that is now, residential customers are starting to buy these. So we're getting into the domain of where we can power our homes from batteries, and ultimately that doesn't help you if the electricity is coming off of a fossil fuel driven grid. But if we decarbonize the grid, then the sort of developments we're seeing with battery technology opens up a whole bunch of possibilities, including transportation, because then if we're powering our cars off of a renewable grid, then once again, then we're not just dealing with emissions in the power sector, but emissions in the transportation sector. And when you add power generation and transportation, then that's more than the majority of our carbon emissions. So, yeah, I think we're moving in that direction. I think folks like Elon Musk and other sort of outside-the-box thinkers are really helping push that along. And nobody believed that Tesla could be as successful as it's been, and he proved them wrong. SpaceX didn't go so well, but he's had a number of other major victories.
I have two things. One, I'll be very brief about this. The electric current which is stored in a battery is direct current. The kind of power that we use in our homes, our industries, all over the United States and every other advanced society is alternating current. Sure. And the direct current from a battery can be converted to alternating current by various devices, but in the process one loses a very great deal in efficiency because of the energy absorbed by the apparatus which manages the conversion. In all of these cases, I think one is limited. The production of batteries, by the way, is hugely expensive and generally highly polluting. It requires major mining efforts, which is very polluting, and so on. Question number two is something that has fascinated me personally for many years, is the possible development, we're not there yet by any means, but the possible development off on some horizon of controlled thermonuclear fusion as a means of producing virtually unlimited amounts of usable electricity, where the fuel would be seawater, which would be reintroduced into the ocean with no pollution, and the byproducts would be lithium and helium, both of which are usable and non-polluting. What are your feelings about the prospects for eventual development of controlled thermonuclear fusion as a source of replacement electric power?
Yeah, I mean, cold fusion would have been great. That didn't quite work out for us. But conventional fusion, there has been research for decades. I actually visited the Princeton Plasma Lab a few years ago, and they gave me a tour of their facility. And they talked about sort of the state of the art of fusion research today, and they're understandably pretty bullish. Of course, one of the criticisms of the fusion community is that they're always telling you we're 10 years, it's 10 years off, and they've been saying 10 years off for quite a while now. Now they really think, and there's this there are proof of concepts like ITER, this reactor in France that's been built that is large enough that in scale that it can, the critical challenge has been to get more energy out, obviously, than you put in, which is described as Q, the ratio of out to in. And obviously, you need Q greater than 1 for it to be viable from an energy standpoint. The argument, as I understand it, is that to be competitive with other forms of energy, you probably need a Q closer to 10. And so the question is whether they can get not just a break-even point, but substantially above the break-even point because of the cost. And you are talking about large investments in infrastructure to build these. And so one of the things that I find interesting is that I think that nuclear energy may very well be part of the solution. Now, of course, fission, that's highly controversial. Fusion isn't there yet. One thing that has always struck me as interesting is that some of the opponents to renewable energy will say, well, they don't like the economics of it. And then they'll point to nuclear energy, but the economics of nuclear energy are a lot worse because you need major government, infrastructure spending to do it. So I've found that there's sometimes a disconnect between people who don't like renewable energy as an option and who do seem to like nuclear. But I think it should be on the table. I mean, that's the debate that we should be having, right? What's the role of nuclear energy in our energy portfolio moving forward, finding that bridge to 2050 when we can be, maybe at 100% renewable energy. That's the sort of debate we should be having in Congress right now, but we're not anywhere close to that because we have a Congressional Science Committee that denies that climate change is even real, and we've got to get past that.
Yes, an extension of the comment you have made about physicists or scientists and experts and authority and so forth. You see the public, as I see it, I'm a forensic scientist, an engineer, and what happens is that you can show something like this, one expert can show something like this, and it's very convincing, persuasive to the jury, even to authority. But another expert come in and give it a different slant completely.
Right. Yep.
And when I hear a lawyer calling me and saying, I have an easy case, doctor, very simple. It's the evidence speaks for itself. Well, they do that generally to make sure that the fees don't go up, making a fuss of the case. But it's really, I came to the conclusion that it is true. The evidence does speak for itself. But most of the time it says different things to different experts.
Right. Yeah, it's a real challenge. And sometimes I think it speaks to a larger problem that we have today in our discourse. It's sort of, we've lost some of the good faith that our public discourse had, decades ago when we had, honest brokers, we had trusted voices, when Walter Cronkite, I'm old enough to remember watching, CBS Evening News, and when Walter Cronkite said that's the way it was on October 19, 2015, everybody accepted those facts. And we could differ in what our opinions were, what we drew from those facts, but we at least started with a common set of facts. We've lost that now. We have this fractured media environment where people get trapped in a bubble of biased media sources that reinforce their own misconceptions and preconceptions, and that makes it very difficult to have the sorts of good faith discussions we used to have. And so you're absolutely right, where a senator can point to a whole bunch of credible sounding talking points and some authoritative platform from which they supposedly come to advocate a view of climate science that's actually at odds with the laws of physics as we understand them. But it doesn't matter because there's a whole cable news network that's willing to provide a megaphone for that misinformation. There are, the Wall Street Journal editorial pages is a megaphone for that sort of anti-science misinformation and disinformation. And so, there's this famous, this famous statement by former New York Senator Patrick Moynihan: "You're entitled to your own opinions, but not your own facts." And today, unfortunately, when it comes to matters like climate change, people feel, in many cases, they're entitled to their own facts. So, do I know the solution to the? The solution is the loss of good faith in our public discourse, and that's a larger problem that I don't know how to solve, but at least we can try to focus on solutions to subsets of that problem and maybe still make some progress on issues like climate change. Thanks.
So thank you very much, Mike. I think we really are all leaving with lots more information, lots more facts about climate change, and hopefully some more inspiration as far as what we should do next. So thank you all for coming, and let's thank our speaker one more time. Yes. Safe home. Do come back again.